Well, good afternoon, everyone. We want to maximize Donna's time, so I'll get started because, I can be long-winded. I am extremely excited to formally present to you our colleague, Donna Blackmond, for today's Faculty Club lecture. So this audience is a collection of family and friends and colleagues, and it seems more appropriate to me, at least, to put a personal spin on things. We all know that Donna is simply the best in her field. And in my view, she has reinvigorated physical organic chemistry and made it exciting again. Her techniques and insight have led to tangible advances that are used on a daily basis in the pharmaceutical industry. Her inventions have been commercialized and cemented into textbooks. She has won numerous awards, as you can read about in this slide, and was the first Scripps scientist to be elected into the National Academy of Engineering, a prestigious collection of elite scientists and engineers. She sits on numerous scientific and editorial advisory boards and is a consultant to a dozen different companies. But this is a story that all or most of you know, and it's the one you can definitely read for yourself. So Donna's untold story is one of overcoming adversity and skeptics combined with the bravery and tenacity to constantly exit her comfort zone. Donna is as tough as steel, perhaps as a consequence of being born in the famous steel manufacturing city of Pittsburgh. Her father, an electrical engineer, insisted that all of his children should also become engineers. And luckily for us, Donna took his advice, receiving her bachelor's and master's degree in chemical engineering from the University of Pittsburgh in 1981, followed by her Ph.D. from Carnegie Mellon only 3 years after that. She began her independent career at Pitt in 1984, and in 1992 she was named as the BP America Faculty Fellow. In 1992, she left the comfort of her tenured position at Pitt and joined Merck as an associate director. At this point, she took it upon herself to learn organic chemistry on the job in one of the most high-pressure environments that exist, Merck Process, a veritable snake pit of synthetic organic chemists. Under the tutelage of Ed Grabowski and Paul Reiter, she went from being unfamiliar with the term enantiomeric excess to revolutionizing the way Merck interrogated reaction processes and eventually solving one of the greatest mysteries of life in the origin of biological chirality, something we will hear a little bit about today. In 1995, she left her comfort zone again and the team she built up at Merck and returned to academia, this time in Europe at the famous Max Planck Institute in Germany. She went from not speaking a word of German to eventually delivering lectures completely in German. After establishing a vibrant group there, she moved in 1999 to the University of Hull in the UK, where she was a professor and chair in physical chemistry. In 2004, she moved to Imperial College as a chair in catalysis. In 2010, we were lucky enough to lure her to Scripps. Now, since Shakespeare is Donna's favorite author, I mention this quote since we all hope she has found her now permanent home. Please do not leave. Of her many contributions to the field of physical organic chemistry and catalysis, I'd like to point out the profound importance and impact of her work that her group has made over the years with the invention of reaction progress kinetic analysis. You can find a very beautiful write-up on Wikipedia. This technique has allowed chemists for the first time to rapidly and reliably obtain critical information about a catalytic reaction in a simple graphical format. They say that simplicity is the ultimate beauty. And Donna has devised this method to demystify the incredible complexity of catalytic organic reactions with the resulting information allowing chemists to both rapidly understand and improve a transformation. This is now a widely used technique in both academia and industry, but was initially met with skepticism. The technique is so popular that even Tony Blair, the prime minister at the time, was caught performing it. Here's another photo where I think Donna is correcting his interpretation of the data, but I'm not quite sure. Since moving to Scripps, several of us have had the great opportunity to collaborate and learn from Donna, including our group. We have published several papers together, and our countless meetings and interactions have been extremely enjoyable. She is drawn to seemingly intractable challenges, never overinterprets data, and is rigorous and scholarly in her approach. Her ability to see organic chemistry simultaneously as being both a mixture of physical and mathematical phenomena is truly awe-inspiring to observe. So Shakespeare said, "Virtue is bold, and goodness never fearful." And I think Donna certainly lives by this mantra. and is not fearful about correcting literature and setting the record straight, as you can see from some of the titles of these highly cited and read papers where she decisively and lucidly debunks myths and misconceptions in organic chemistry. Now, in closing, while researching the name of Blackmond, I could only find this coat of arms and decided to make up my own synonyms for the word. I think that anyone that knows Donna would agree with these 8 descriptors. I do find it humorous, however, that the family symbol also matches the colors of Where's Waldo. That's strange. It appears to be quite a bit of a theme. Maybe we should add boisterous to the list of descriptors as well. Now, I'm not telling my source, by the way. No proper introduction of Donna would be complete without mentioning her gifted son, Daniel, who is well on his way to becoming a rock star, like his mom, but in the field of music. Lastly, very few people know that Donna has superpowers that were only recently revealed in a group dinner after approximately 3 pitchers of margarita. Apparently, she has a natural, extraordinary capacity to remember numbers. In fact, she has remembered all the telephone numbers she has used in her entire life, even the ones from schoolmates, as well as the numbers of all the credit cards she has had in her entire life. I leave you with a warning to never show her your credit card. Otherwise, she will involuntarily remember the number forever. With that, I will turn the floor to our beloved colleague, Donna.
Thank you very much for a very kind, and I think I got off easy introduction from Phil. I'm glad that he didn't find any pictures of my H hair index from the 80s when I had big hair. So at least I escaped that one. And since you mentioned Shakespeare several times, I'll just tell it, for anybody that knows anything about Pittsburgh and people from Pittsburgh and their lack of grammatical skills, Shakespeare's, Hamlet's famous soliloquy would have been "or not." So I'll leave you to think about that if he was born in Pittsburgh. So to get started, I'm going to tell you a little bit about some work that we've been doing actually over more than a decade now. We started this actually just before I went to Hull, so it's spanned several different of the places that I've been in the last few years. And it's a problem that is actually one of the sort of a large problem and an intriguing problem in science that seems to fascinate chemists, biologists, and lay people as well. The property of molecules or objects to be mirror images but non-superimposable. And it turns out that it's in chemistry, it's in literature. This is from Lewis Carroll's Through the Looking Glass, and where Alice, as she was thinking about this, famously wondered whether her cat, Kitty, would be able to drink the milk on the other side of the looking glass. And actually, Kitty wouldn't be able to because the sugars would have been in the wrong hand, and it would have been probably poisonous for the cat. So it's something that fascinates people. And it seems to be key to the origin of life, the chirality of biological molecules. Most of us remember the story of Louis Pasteur finding the crystals of the disalt of tartaric acid and realizing that they had this hemihedral structure that were mirror images. And he painstakingly took tweezers and separated them into 2 piles, dissolved the piles separately, and realized that they rotated the plane of polarized light opposite directions. And so this was the first real indication that there was something about this mirror image property that was quite interesting. That was actually about a quarter century before we understood that molecules themselves had chirality. This was object chirality in that case. But since then, of course, we know that molecules and informational polymers that go into proteins and DNA have this property of single chirality, one hand or the other, and it seems to be important for molecular recognition and therefore of life. about 10 years ago, when I was still in the UK, they did a sort of an overview or a report on chemistry in the UK, and George Whitesides was in charge of it. It was called the Whitesides Report, and he was trying to exhort them to spend more money on this kind of research, which they haven't done. But he said that this, the origin of life is one of the, he was saying that this is something the chemists should be working on more, not just biologists, because it's prototypically a molecular problem, he said. And it's really a problem of increasing complexity, which is actually humbling when I think about the part that we're working on. Homochirality of molecules is really quite small and early on the way of the whole problem of this increasing complexity, self-replication, compartmentalization, and all the tasks that have to go on to create life. And George puts it a little bit differently. If you talk to him, after the meeting in the pub, he'll say, it's a really long way from slime to Mozart, and we have to figure out, we have a lot of different problems to figure out. So it's I try to remember that as a humbling thing when we realize that we're working on a very small part of this problem. But the big question really about the chirality of biological molecules is, how do we get from here from there? Because if you think about the prebiotic soup, the first carbon-carbon bonds that were being formed, there doesn't seem to be any reason they would go one way or the other. Basically, and if you go into the laboratory and try to make an amino acid without any template or catalyst, you would make 50% of each left and right hands. So the question is, how did that first get started, and how did we get to where we are today? And we're going to talk about an enantiomeric excess. I had this slide for the chemical engineers I gave a talk at the induction at the National Academy, so they don't know terms like EE or L and D for R and S and left and right, and S and R. So I have them on the slide for definitions. So the problem has really two parts. First, you have to break the symmetry. You start out with an equal number, and you've got to somehow make that symmetry break. And after that, that's not enough, really. You have to propagate that. You can't let it go back. You have to make sure that you can increase or amplify that asymmetry that you create. For a long time, people thought mainly about the first part, the symmetry breaking, but that seems to be pretty well understood, that even stochastically we can get an imbalance. And in fact, if you think about the trivial solution, is every time you make an odd number of molecules, you have an imbalance. But we have to find a way to keep that imbalance from writing itself. And that's the part that we work on, is the amplification process. And so basically, we've looked at a range of approaches to this problem, things that could have happened, everywhere from chemical properties to physical properties. Essentially, when you make a joke, which is actually not, I guess I could do it here, but some areas it's bad to make jokes like this. I used to say that God was also a physical chemist as well as an organic chemist, but in any case, this puzzle of chirality, for a long time, there was absolutely no experimental data. Until the last decade, really, of the 20th century, there was nothing experimentally done in this area, and it was really mainly theories and modeling, essentially computer simulations to try to understand it. But since then, there's been a lot of work, some from our group, some from other groups, and we've actually come up with 4 different sort of vignettes that ways that we might have come from a prebiotic soup that was racemic to get to where we are today with single-handedness. But I'm not going to tell you about all of them. I used to try to cram all of this into one talk, but now I'm going to focus on 2 vignettes. One from the very beginning that we started to work on, we're still working on, which is closer to the chemical side, and then one that's a physical model that relies on phase behavior of chiral molecules. So I'll talk about each of these 2 vignettes. So we'll start out with the chemical model, which talks about autocatalysis with chiral amplification. And this came from a paper in the mid-20th century. 1953 was a pretty good year for origin of life type research. And Frank was a professor at Oxford and then at Bristol. When he did this work, he was at Bristol. And he basically wrote this theoretical paper with some simulations. And he said, in words, what his model said was that if you have a chemical substance that can make more of itself and prevent its other hand from being made, somehow suppress that, that's all you need. It's a simple and sufficient life model to get from here to complete enantiopurity or homochirality. So he had the equations, he graphed all the results of his equations, but the last sentence of the paper was what caught a lot of people. What he said was, an experimental demonstration may not be impossible. This is a theoretician talking, right? And so organic chemists read this paper, and that's Hans Windberg was a scientist in Groningen. He worked on this problem for a long time and wrote a number of review articles, and what he said was, now that statement, that's a challenge to any red-blooded chemist. If some theoretician tells me that it might not be impossible, I'm going to be the one to find it. And so a lot of people tried to find, think about molecular level, what molecules might be able to do this, make themselves and prevent their other hand from being made. And the challenge was met in 1995. It wasn't Windberg. He was close, but he wasn't the one who discovered the system that does this. And this is a reaction by Kenzo Sowai. It was published in Nature in 1995. And a few years ago, the Nature editors talked about, they made their list of their top 50 papers of the last 50 years, and this is one of the ones they picked. It's a dialkyl zinc alkylation, so it's an interesting reaction, but it's not very prebiotically relevant. You really couldn't do this in an aqueous soup. But basically, the product catalyzes the reaction. You can start out with almost no imbalance between, you can put the product in with almost no asymmetry, equal numbers of left and right, and it amplifies EE over time. So it was a really interesting finding. It was really one of the first experimental systems that we could think about how we might have got from there to here. Sowai has gone on to show this with amazing results. You can instigate this reaction. You can initiate it using chiral quartz. You can actually initiate this reaction with an initiator that's with the product being chiral only in isotopically chiral, where a carbon is 13 versus 12. And that's the mirror image difference. So it's a tiny, tiny energy difference between those molecules. So it's fascinating, but there was no work actually done to try to understand how. Does it fit the Frank model? How does it work? And so we got into it about 4 years after this was published. I thought about this, and I realized that kinetics were going to be really important in this kind of reaction. An autocatalytic reaction where the catalyst is, you're making itself. You can't really do the classical kinetics that you would do as an organic chemist. Initial rate studies wouldn't get you very far when the catalyst is changing all the time. So we actually carried out experimental studies of this reaction using reaction calorimetry, which was one of my favorite tools. And we initiated the reaction with the catalyst at different EEs. I'm showing you two plots here of 6% EE, so almost equal amounts, and then 22% EE. And we built a kinetic model, which we fit to the data, to the kinetic data, the reaction rate data, and then we could predict from that what the enantiomeric excess should be as a function of conversion. But we don't just have to predict it, because we can actually go back and take samples of this reaction and measure the EE by HPLC, which we did. And that's what we got. And so we were quite pleased. That's not a line through those data points. Those are two independent. One's a prediction, which is completely independent from the experimental data, which are in pink. So as a kineticist, it was really gratifying to see that you could predict from the kinetic data what the selectivity was going to be, which is usually the opposite. Usually the kineticists are telling you why something happened and not what will happen. So we were happy that we were able to predict rather than just rationalize. So just briefly, what the model says is that you need some kind of nonlinearity, really, to get this amplification. One way to get nonlinearity is to make higher order species, dimer monomer equilibrium, or even higher order species. So we made a model where we make the product makes dimers, and if the catalyst makes an R product, and it's driven to become a dimer, and it looks around. If it sees an R, it makes RR. If it sees an S, it makes SR. And it does that with equal, it has no preference for R or S. It's stochastic formation of dimers. And you can write a dimer equilibrium constant. And actually, our model predicted K equals 4, which is the stochastic division between the dimers. And again, it was gratifying that a couple years later, my collaborator John Brown was able to get NMR spectra of these dimers, showing that if you have a racemic mixture of 4 dimer molecules, if K equals 4, basically you have 2 heterochirals, SR squared is 4, and then 1 RR and 1 SS. And so that's K equals 4 means equal numbers of homochiral on one side and heterochiral on the other. And so that's clearly what the NMR is also showing. 48 to 52 is close enough for me. So the other part of the model is that these dimers are going to be catalysts. And it turns out that the RR and the SS have to have the same rate because they're enantiomers. But the SR, the heterochiral dimer, doesn't have to have the same rate. So the model fitting the data to the model gave us what the relative rate, this constant G, of the heterochiral dimer. It turns out it's inactive, completely inactive. So that rate doesn't go at all. And so basically with those two equations, we could, every time we convert a molecule, we can then calculate what the new EE is when we make a new product molecule, and then we go back and we do the reaction again. The model does this, and it continues. And so the K equals 4, G equals 0 was essentially all that. This is a very simple model, but it explained a lot of data. And so just to put it into a cartoon or words, it really, the key to this model is this inhibition part of the Frank model. You have to be able to stop the other guy from being made. If you've got a major and a minor catalyst, the R catalyst, what you want to happen is you want it to go back and make itself. R makes more R. But if you make a mistake, even once in a while, and you make an S is going to go and make S. And when it does that, it'll make more S than it does R. And it turns out that there's a derivation in the supporting information of that paper if you're interested, but you can show mathematically that you can't win. In fact, you're inexorably going to go to zero, no imbalance at all if you ever make a mistake with a simple model like that. You have to have some way to skew things. And that's what the dimer formation helps us do. And our dimer that's inactive, essentially, if we can siphon off some of the S, doesn't even have to be all of it, but just some of the minor enantiomer that we make as a mistake, if we siphon that off into this heterochiral dimer, and in our case that dimer is completely inactive, it's just a dead-end reservoir, then what that does is it prevents that S molecule from going back around and making more of itself. So you can get amplification if you have some way to sequester whenever you make a mistake and make the wrong hand, you have to have some way to sequester it, and that's what the heterochiral equilibrium does. So it fits the Frank model, and it's really still the only chemical reaction that does that. And it's not prebiotically relevant because it's dialkyl zinc chemistry. So there's actually quite a bit of work being done still, the holy grail really for people in this area is to find an organic reaction that has those properties. And we're working on it. We've got 2 grants actually to work on it. And it's one of these things, my students are here, but it's a little bit worrying that somebody thinks that people haven't found in 50 years a Ph.D. student is working on. But anyway, we have some pretty good ideas. We are making progress. So that's all I'm going to say about the chemical model, and I'm going to go on to the chiral, what I call the chiral amnesia model, which I'll explain the wording, the name of that in a minute. And it's a model based on physical phase behavior of molecules. So the story starts out with something that really doesn't seem to have much to do with origin of life, biological chirality, or even organic chemistry. It starts out with sodium chlorate. Sodium chlorate is not a chiral molecule, and it's not even organic. It's an anionic salt, but it turns out that it crystallizes. When it makes crystals, it makes mirror image crystals, left and right crystals. So it's a very interesting system. A lot of people have thought about sodium chlorate since the beginning of the 20th. The turn of the 19th to the 20th century, people were writing papers about this molecule. Van Hoff was one of the people. He was worried about its implications for the phase rule. I'm not going to talk about that, but anyway, it's an interesting molecule. If you think about it, you can make left and right hand crystals. But if you're in equilibrium with a solution phase, dynamic molecules jump on and off crystals all the time. If you're in equilibrium, when a sodium chlorate jumps off of a D crystal, it doesn't remember that it was a D. It equally could go back down when it goes back down onto a crystal onto an L. So that's what made this system interesting. So this guy, Cristobal Viedma in Spain, looked at this system. And he's a geologist. He works at University Complutense in Madrid. And he usually worries about water on Mars, and he digs into the ice in Antarctica. He sends me photos when he's waiting for the boat at Tierra del Fuego to take him to Antarctica. But he just got interested in this problem, and he just tried something that was a really unusual thing to try. He took a system which is at the end of a crystallization. If you would crystallize sodium chlorate, you get a supersaturated solution, you cool it down slowly, you'll get half left, half right crystals. Mostly. I mean, you can. Most of the time, you get half left. That's what you expect: half left, half right crystals. So he took that system when it was done crystallizing. So there's no net movement of molecules anymore. This is at the end of a crystallization. It's dynamically molecules are moving back and forth, but there's no change. Right? Nothing should happen. You could stir this forever, and nothing should happen. So then he did that same experiment, and he put glass beads in the vial, and he stirred it with glass beads. So he's grinding the crystals while he's stirring. What should happen? This is we're at thermodynamically stable state. It's we're at equilibrium here. Well, what happened was every time he did this, within 24 hours, all the crystals turned left or all the crystals turned right, and it was completely random. If you do 10 times, 5 times they go left, 5 times they go right, but it went inexorably every time, and there doesn't seem to be any driving force to make these guys change, from one to the other. And he took him about a year to get it published. Physics Roulette's a pretty good journal, but I think he tried some chemistry journals, and they said, this is just crazy. It doesn't happen. And after it came out, a lot of people, didn't understand it either, and it caused a lot of sort of interest once people found it. I mean, typically a lot of the organic chemists are not reading this journal, but then people started to think about this problem, this system, and it became interesting. Basically, if you've on the left there, the molecule's achiral, sodium chlorate, but the solids are chiral. But basically what's happening in this system is that you use that solution phase as a conduit between the two solids. Basically, one solid goes to the other via the solution phase. You don't turn one crystal into the other. Molecules come off the crystal and they end up on the other one. Okay, so that's we know a lot more about this now, and that is what's happening. But when people were first looking at this, there were people writing things like saying this is an example of chiral recognition on the nanoscale, and I thought about it. I said, no, that's not what's happening here. This is actually chiral amnesia. The molecules are forgetting that, when AD jumps off a D crystal, it forgot its chiral past, and it has a new chiral destiny available to it, D or L. And that's essentially what's driving this, is that forgetting, the amnesia. So a lot of people thought about this, and basically then you make the leap. What if we had chiral molecules that crystallize separately as D and L, like Pasteur's tartrate? What if we, that are also chiral when they're in solution, intrinsically chiral molecules? How can we make them forget their past? Okay, how does a chiral molecule forget its past? All the organic chemists know this, right? It's the bane of organic. If you're trying to make a chiral molecule that's a drug for Merck, the last thing you want it to do is to forget its D and turn into L. It's racemization. Okay, that links the D and L in solution. D's and L's turn into each other via this isomerization between the two molecules. We usually don't want that to happen, but here the paradox of this is that forgetting, that racemization, that erosion of EE is actually what's driving the approach to enantiopurity. And I'll explain why that's happening, or how that's happening. But basically, the same thing can happen now. Now that we have that link between L and D in solution, if that's going fast enough, it's exactly the same as a sodium chlorate system. And Ds can become Ls in solution and go through the conduit of the solution phase to L, or vice versa. So we weren't the only people that realized this. A lot of people did, and there was this real search on to find an intrinsically chiral system that would do this. And I had colleagues in that I was we hadn't collaborated yet, but we were trying to think of ways to collaborate on other phase behavior stuff that we were doing. Richard Kellogg at Syncom and his former student Bernard Kapjan at DSM Pharma. And so we basically said, we got to find, let's screen for some molecules that might have this, that might work, that have the property that they crystallize separately as L and D, left and right crystals, and that we could racemize in solution. And we found this one. This is one of the first ones that we did. It's a amino acid derivative. It's a phenylglycine amide Schiff base. Schiff bases are a little easier to racemize in solution than amino acids are. So we can make it go back and forth in solution, and it crystallizes as two separate solids. And so we tried it. It took us a while to get the conditions to make it work, but this is what we got. Essentially, you have a small imbalance, a little bit more left or right, and it completely goes. Over time, it takes some time. And in fact, the Dutch student who was working on this was, basically you can see it's sort of autocatalytic the way it's autoinductive. It gets faster and faster, and it goes. And once it's all the way done, it doesn't turn around. It stays. And the student, Wim Noordin, who was working on this, said, 7 days, origin of life research, sounds about right. And then we rested, So that was really interesting. And it was written up in Nature News and Views. Actually, Mike McBride at Yale wrote up it's called News and Views. It was one sentence of news, and then the rest was his view of what's happening. And I'm going to tell you my view, and we don't agree. So there's still a lot of, let's say, vigorous discussion about this system. But that was a nice comment to have somebody say that this was this is essentially the most original thing that since Pasteur used his tweezers. So, but it's a really interesting system. So what is happening? What do we think is happening? Well, I think that it's based on pure physical chemistry. I don't think it's magic. Some people like magic, but I like physical chemistry. Small crystals disappear, big crystals grow. Gibbs-Thompson rule. Ostwald ripening is really a corollary of the Gibbs-Thompson rule, but basically you know this from looking at drops of water on a window. Small drops evaporate faster. You're trying to reduce surface tension, okay? And it has the same thing between solids and liquids. Small crystals have higher solubility than big crystals, and so they dissolve. Big crystals have lower solubility, and they want to grow. So basically, thermodynamics says we go from small to big. That's thermodynamics, okay? But that doesn't say anything about chirality. But we know that, so we're grinding these molecules. We grind them, and so we get smaller and smaller particles. We get slight supersaturation in solution. Some of those molecules in solution may see a big particle that didn't happen to get ground up, and there are too many molecules in solution for that guy. So they go down onto the bigger particles. So molecules that dissolve via grinding are going to seek out a bigger particle to go back onto as in the solid phase. So if you even by chance, if you have a slight difference, the stirring bar, there's nothing symmetric about the stirring bar. The stirring bar may have missed an L crystal, and there's a bigger L crystal. The molecules in solution are going back and forth L and D. The L's go down on here, D's push over to L in solution. Molecules from the smaller crystals go up and over. It's self-reinforcing, and it's all based on physical chemistry. So, so does it make any? This is the problem. This slide is the problem that people have with this. This is aspartic acid. Actually, we've also now done it with. This is a proteinogenic amino acid that also we've published a paper on this system as well. But this system should be perfectly balanced, right? If you have enantiomers, the rate constant for them to go back and forth in solution is 1 to 1. They have exactly the same solubilities. They're enantiomers. This system is perfectly in balance. So why does anything move? Well, you have to remember what we just said. Basically, what if one's big and one's small? Now they have different solubilities. Basically, smaller crystals dissolve, big crystals grow. We created an imbalance. Gibbs-Thompson helped us create an imbalance in this system. And if that happens, then the driving force for the net movement of molecules is just this crystal size induced difference in solubility, like that. This is actually the same thing as what in the title is called Dimroth's principle, and people in pharma companies know this very well. It's exactly what you do all the time with diastereomers. You crash out the less soluble diastereomer, and it's exactly that process that you're using. You convert them in solution if you've got it's like a dynamic system, and the only problem here was that we shouldn't have had a difference because they're enantiomers, not diastereomers, but we created the difference. So I think that's all we need to explain it. But anyway, so we've looked at a number of other molecules now, and I showed you, this is actually from the same family as that first molecule, but this is actually the molecule that makes Plavix. It's a BMS blockbuster drug. It's very similar. It's also a phenylglycinamide Schiff base. But now that we're on a pharmaceutical time scale, we're in hours and not days. But so we did 24 runs, and 9 go right, 8 go left, 7 stay racemic. That to me is random. Okay, if we tried to start out with a racemic mixture of crystals, and as close as we could measure, it was racemic, and they just randomly do what they want. So it seems to be stochastic. Something triggers, and they have different times that they take. They don't all take the same time. We started with the same batch of molecules, and just ran 24 different runs. Something triggers it, and we think it has to do with particle size, right? We think we get a difference in crystal size. So let's think about all the processes that are going on. There's chemical and there's physical processes. So we have to think of how fast each of these things is going. We've got a chemical reaction in the solution phase, and we've got physical mass transfer between solution and solid. So the first thing we think about is the racemization rate. And for this molecule, it's about 2 minutes, the half-life. So it's pretty fast on our scale of hours. So they go back and forth in solution. This rate here is pretty fast, okay? So we also know that the dissolution kinetics are fast. The rates of going up and down, just if we looked at any of them by themselves, they go up and down. You can saturate a solution really fast. So that's also fast. So what if we could tag a molecule? What if we could take a guy that's embedded in the middle of an R crystal and follow him, because he might go up in solution. He can become, this R molecule here can become, he can go off the crystal, he can racemize, he can come over here, and he can come back down here. If we can put a tag on him and follow him, we can measure how fast those processes happen as well. So we did that by making, we basically tagged with nitrogen 15, the amide nitrogen, of one, either the R or the S. We did it both ways. Everything was done both ways. But basically I'm showing you with the R solid, the R solid here was completely nitrogen 15, and what happens over time. Essentially within 3 hours, you could be anywhere. If you started in the middle here, you might be in the middle here, you might be here, you might be here, you might be here. It's completely mixed, completely washed through. The memory of where you started is completely gone in terms of the nitrogen, the nitrogen on this molecule within 3 hours. Okay, so that's just the move. That's not the net movement. That's not going to homochirality yet. That's just what happens to one molecule that we're watching, or any molecule that we watch. They're all mixed up. So how does that relate to the changing EE? Well, in this case, basically to make we know they're all mixed up, but to make the S go over to the R, that's basically what happened. So everybody was mixed up before this process really was just getting started. So they don't, the mixing up of the molecules is not the same as triggering the move to homochirality. And in fact, we've done this. We did 4 runs with this system, where we started with the nitrogen 15 on either molecule. 2 of them stayed racemic, 2 of them went to an antiopurity, and they all had exactly the same mixing up profiles. So this guy here never stayed racemic to 5 hours, but all the molecules, all the ends, the nitrogen 15s are completely mixed up, even though he didn't lose his solid. So there's something about how this gets triggered that, it's just completely random how it happens. So we looked at that a little bit more closely. We had help here with measuring crystal size distributions. We can't really measure on the low side, but we can get this half of the distribution. Okay, so these 3 runs. Here's one that went right, one that went left, and one that stayed down the middle. And they all started, we just took crystals out of the same pot, so they all have the same initial crystal size distribution within our mirror of measurement. Then we looked at, again, we took a sample at 5 hours, right after it plummeted and went to homochirality. And what happened? The one that stayed down the middle stayed with the same narrow crystallite size distribution. The 2 that went left and right got broader. So that looks like that seems to me to be proof for this. Somehow we instigated a crystal size, the growth of the crystals made this movement start, and it's self-reinforcing once it gets started. And then eventually at 8 hours, these go back to the original distribution, because that's really where the thermodynamics wants. But there's this transient kinetic effect of having a crystal size. And you know this from doing crystallizations. If you have a saturated solution, supersaturated a little bit, and you throw a crystal in, you can see the molecules glom onto it. And somehow that happens under the, as the reaction's going on, as the crystallization's going on. Okay, so this is the slide just to, give you my credentials as a chemical engineer. We're also doing modeling of this. We can model this by using the Gibbs-Thompson rule to model the crystal growth rate. And we have a breakage term in. We can put in various ways of breaking the crystals into 2 daughters, 3 daughters, random sizes, or split them in half. And we can account for the sigmoidal shape of the curves. We can account for a lot of different issues. And we can follow, essentially, computationally, the change in the crystal size distributions. So that's I think that's giving us a lot of insight into basically that's all we put in this model was this Gibbs-Thompson rule. We didn't need magic. The magic that other people are trying to talk about in this is they think that there's the need for some nascent subcritical clusters of molecules that have to add rather than molecule by molecule. So something that we can't measure is causing everything that we see, is what they say. But anyway, I think that we don't need it in the model, and I don't think we need it in the experimental data. So I think that's, yeah. Okay, the last thing I want to talk about was just coming back to Pasteur, actually. We thought about this. We can't really control this in one pot. We don't know how to tell one particle to stay big, to be the one. It's a random thing. But we might be able to split this into 2 pots and stir one pot really hard so that we make really small crystals, high solubility, and have another pot with bigger crystals and low solubility. And we might be able to use this to separate the enantiomers. Rather than convert one to the other, maybe we can actually just do a separation as well. And we had this idea, and basically what we were going to do is basically this pot we're grinding with glass beads, so this high solubility here, so there's lots of molecules in the solution phase. Over here we've got just a small amount of one hand, only one hand of the crystals. Here we've got both, we've got a racemic mixture. And now we're not stirring very hard, so we have low solubility. We can measure there's about a 10% difference in solubility between these two pots. Then we connect them, and we pump the liquid back and forth, but we've got filters so the solid can't move. Solid can't go anywhere. Solid has to stay in its pot. So what happens over time? What if we let this go back and forth over time? Okay, so the day that we did this, basically Jason Hine, a lot of people here may remember Jason. Jason was going to try to come, but I don't think he made it. But anyway, he's a professor at UC Merced now. And so 24 hours later, that's what we got. Basically, all the blues in this pot are, turned into pinks and went to this pot. Well, all the pinks in this pot went over and became pink over here. They went through the solution phase. They weren't solids. Now we're not racemizing here. There's no base to try to racemize. Tartaric acid's hard to racemize. So this is purely a separation between the two. But it's actually a very viable separation method. It's sort of like Pasteur's tweezers. And in fact, the day that we set this up, we thought of this experiment, and I said to Jason, we have to do the tartrate. That's the one we have to do. We've done it for other things like threonine, proteinogenic amino acids, but tartrate. So I came into my office that morning, and this was on my desk. I don't know if you can see. It's a pile of crystals and tweezers, and it says, Donna, you could start on this batch, and I'll race you. And I think he probably would have beat me if I had actually tried to separate them. But anyway, so we think it's a nice sort of take on Pasteur's tweezers to separate it using purely solubility differences. It's isothermal. We're not using temperature gradients to do this. So that's pretty much it. I just have one slide about a couple other prebiotic scenarios. One was I was sitting back in England, actually before I moved here, and the Sunday paper, The Guardian, had a full-page ad. It said, "Girl discovers prebiotic in cereal bowl." Like, oh no, I've been scooped. And I don't know if we use this here, but in England they use prebiotic is what you feed the probiotic bugs. The prebiotic is what they eat. Anyway, she's from the University of Reading. You can't see that, but she's discovered all this stuff, so I'm panicking, and I sent it to Cristobal Viedma, my friend in Spain. I said, look, she's scooping us. What are we going to do? He said, don't worry, we've got something better. This is what we've got, prebiotic soup. I don't know if you can see, it says, cooked by C. Viedma with LD ingredients. So I have this picture of like alphabet soup with only L's and D's and no other letters. So that's pretty much it. I will stop here and just thank, the stuff I've talked about, it really took place over 3 different places that I've worked, University of Hull, Imperial College, and Scripps. So I haven't cited everybody, but I tried to cite the most important people, at least for the things that I mentioned today. And also, of course, the money is important. And we've just been very lucky to get the Simons Foundation collaboration on the origin of life, which I think is going to be a real boon to research in this area. And of course, I like to show this to people outside La Jolla. They think we always have nice weather. They don't, not on days like today, but this rainbow I thought was quite lovely. It starts at the chemistry building and ends on the nice sculpture of the Flame of Knowledge. So with that, I'll stop. I guess I'm not supposed to take questions, but I'll be happy to talk to anybody at the reception.